quick NSX EVPN workshop. NSX-T now supports EVPN as of version 3. We'll work through configuration with an upstream Juniper router as well as our example PE router inside our data center. So EVPN is the focus of this. So a quick recap on my lab environment as well. Inside my lab I have an NSX fabric. NSX natively provides a UDP based overlay encapsulation across the data center, and we can configure the overlay architecture to use whichever VLAN we like. So in this case my lab environment is using VLAN 208. So every tunnel I build across the network is using the same VLAN ID for our transport layer. I have a couple of hypervisors as well inside my environment. These are ESXi 7 hypervisors. The solution obviously works with 6.5 and 6.7 as well. They have a single physical NIC into my fabric. I could obviously have multiple links and bond these together as well and provide some additional resiliency at that point. So inside the kernel of the hypervisor here is where all our encapsulation takes place for the overlay tunnels, as well as our security enforcement as well. So this is our first hypervisor on the network. This is the second. I could have 2 hypervisors, I could have thousands of hypervisors. Both these hypervisors could be across discrete data center locations as well, so either across the city, across the country, doesn't really matter in our requirements here. And provided we can forward IP from one location, so our IP address here can communicate with the IP address here, then that's a working solution. As part of our design as well, we have an NSX Edge machine. This machine can be either a virtual machine or it can be configured onto a bare metal server as well if we need high-speed connectivity requirements into our network, such as 40 gig or 100 gig interfaces. So logically it's connected into the fabric as well. And because it is an overlay solution, we have essentially a tunnel is formed across the network. And we also have tunnels built into the edge machines as well. So the tunnel we use is called a Geneve tunnel, uses UDP, and there's an RFC for it as well if you want to go and read that. So everything taking place inside the NSX fabric is sitting on top of the underlay network. At no stage do we log into the underlay and actually add additional configurations for VLANs or VXLANs or anything like that. We can have one tenant, we can have 1,000 tenants, they all share the same underlying configuration that is built into the underlay. So it's a very hands-off, low-touch environment for the physical networking components. All the security and networking constructs are pushed into the kernel of the hypervisor platform itself. So we'll draw this. Our edge machine, in my case I have one. I could have a cluster of these edge machines as well, if I wanted to, that are inside one data center or spread across multiple data centers. In my case, I'm connecting to an upstream Juniper MX as well, so I've got a physical connection in here. This is an MX. This is where I configure my VRFs as well, and obviously provide connectivity across the wide area and reachability to the internet. And I do have a peering session taking place as well with my Edge VM. So there's a BGP session between here and here. And I'm advertising standard IPv4 routes and BGP Based EVPN as well. I could obviously advertise IPv6 routes if I wanted to as well, but in my case I'm not doing that. As a transport between the Edge and the MXs would be using VXLAN between here and here, and we allocate a pool of VNI identifiers with inside the fabric as well. So if we want to provision a new customer on here as well, so a new tenant is allocated to the network, we would, let's say we have a customer called customer A has turned up and we need to provision him inside the network. So we're going to provision this all inside NSX-T. So we need to include a couple of things as well. So just understanding how NSX-T is built, the edge machines, the edge VMs that sit down here, they operate using what's known as a tier 0 router. The tier 0 router is our edge routing platform. It's the only type of router we support logically that can actually provide a physical uplink into a physical router, in this case a Juniper MX, and we have multiple what we call tier 1 routers, which are really the tenancies, and we give each of our tenants would normally be allocated their own tier 1 router. Provides route isolation, separate routing tables, and additional services can be built across this to scale the solution out as well. So if we have our tenant called customer A running on here, so we would normally have customer A, we would give them their own tier 1 router. That way we have complete control over the services that customer has access to, the security we can enforce, and we have route table isolation, things like that. The tier 1 routers are logically distributed across the entire solution when needed. So if I had the requirement to deploy this customer's router in both locations, so potentially it might appear here and also over here at the same time. If there was no workloads on these virtualization platforms, then we wouldn't actually configure them. They would dynamically appear if and when a workload was configured on that platform. And likewise, if a machine was vMotioned across as well, we would provision that on demand as well. Right, so the tier 1 router is actually then connected into our tier 0, which is provides the uplink to the outside world. So BGP in this case. And every customer network obviously wants to have a subnet connected to it, right? So we'll call this 192.168.0 will be on here as well. And obviously we could have multiple subnets connected to this customer as well. So we need to go and provision this now with inside NSX. We also need to configure this inside our MX platform as well, just as a really a standard VRF with EVPN protocol enabled as well. So if I log into my MX, we would need to configure a VRF with inside the Junos configuration, just like we would for any other VRF deployment. And let's have a look at our MX here as well. So I've already configured this, as you can see. I've got a VRF called customer A. I've configured EVPN as a protocol inside the VRF. I've configured VXLAN encapsulation for the tunneling mechanism, and I've configured a VNI of 79001. My local route distinguisher is 200.002.100, and I have a VRF target as well for my import and export of routes I'm loading through BGP. The only other thing you have to really ensure you have configured is the VTEP source address, which in my case is loopback 0, which is also the address I'm using for my my route distinguisher as well. For BGP, towards the NSX fabric, I've configured IPv4, so iNet unicast, EVPN signaling, so the prefix is advertised through EVPN, and my upstream peer is 3, and my local address is 221. So .221 down here and .3 up here. I think this was 200.0. Whoops, 0.2. That's my source for my VTEPs. So I just need to make sure we have the corresponding correct configuration now inside my NSX fabric. You can really think of NSX as just one giant router that we configure centrally through the NSX-T manager. There is also CLI under the hood you can get to as well if you want to issue standard CLI type commands into each element of the NSX-T fabric, and you can do that centrally as well and jump across and issue CLI commands as you need to. So if I log into the NSX-T management platform, we have a separate management interface that resides outside of the vSphere environment, and we then program changes back up into vSphere as well, so the vSphere admins can actually access the networks that you're configuring, but you have complete control over the networking and the security enforcement that's taken place. If I look at the topology I have, so we have our peering router, which is this aligns with my diagram, is a tier 0 gateway. It provides connectivity to my upstream MX. I have multiple tier 1 routers, so I've got one called lab, I've got one called DB servers. So we need to define another one called customer A, and I'll connect their segments to this. So the first thing we'll do is have a quick look at our peering router. This is my tier 0 gateway. Obviously it can be called whatever we like, but I've called it peering. I have configured it with a route distinguisher, so terminal 001 is the address I've chosen here as well. So this is up here, 200, essentially that's the loopback address as well. And I've configured the EVPN mode. I've also told it to use a pool of addresses for VNI. So my VNI range, 79,000 to 79,100. And that's it. Okay, we'll close that. So just like on the MX, we configured a routing instance. We would go and configure a new VRF. So we'll add a VRF. I'm going to call it customer A VRF. And I'm going to drop that into my peering router. So we're now configuring this VRF within the peering router. I am going to give it a local route distinguisher 100. I need to set my route targets like I did on my GNOS config. 65,100. 65,100. Whoop. Alright, add that. Apply that config. So now we're building up the same type of config syntax we had. We'll save this. Oh, okay, that's cool. We need to configure a VNI. 39001. Okay. So it does tell us we've been stupid. I'll save that, and right. So we now have a configuration. We've deployed a new VRF within the peering router. We have allocated our route distinguisher, our VRF target, and our VNI. We will ensure that, just like a real router, what routes are we going to advertise upstream, so we have complete control, just like we would with a route map or a GNOS policy. I'm just going to call it all. I'm going to advertise connected routes. I could also choose to advertise the load balance of VIP addresses, our DNS forward addresses, our NAT values as well. Let's just leave it like that. Okay. And now we have configured a VRF inside our platform. We're going to configure this once, and the platform takes care of intelligently configuring this across the entire fabric and across every hypervisor. We'll allocate this customer a new tier 1 gateway as well. So customer A tier 1. And we're going to connect this logical tier 1 routing instance into my VRF. So this is like connecting a patch lead from here into here. And we are going to, we still get control over what routes we want to advertise. There's multiple places we can do this. Let's just advertise connected routes. I think that's all we have to do at this stage, but we probably should configure DHCP as well. We'll bring up some workloads later on and make sure they can actually get an IP address as well. So we have now configured our tier 1. We've connected that into the VRF, and we haven't configured any subnets for this. We call that a segment. So a network segment has several things. We're going to have multiple segments connected for this customer as well, so we can have one segment or hundreds of segments connected into their tier 1 gateway. So let's call this customer A servers. We're going to connect that into here. We're going to choose to do an overlay network. So by choosing an overlay network, we're now sitting on top of the IP fabric, and we're forwarding using a Geneve tunnel. We could also configure this to be spat out simply with a VLAN tag without any overlay if we want to. So if we need to fall in line with the existing layer 3 forwarding and security requirements, we could do that. But for the sake of this, we're going to choose to do an overlay. We're going to allocate address range to this customer as well. So we're going to use this address space. So we configure it with the gateway address as well. So .1 is the gateway that we configure with inside the logical routing instances across the network. And we can also enable things like DHCP as well. So 188. Let's choose this. .10 being the first address. 800 last address. We'll also allocate them DNS server as well. Okay, so we have now allocated a new network segment for this customer. We've connected it into their own routing instance. We have told it to overlay between everywhere, and we've allocated the subnet, the gateway, and configured DHCP services to allocate addresses and also to allocate DNS. We'll save this. So what's going to happen now is, we'll say no to that. This network will be advertised to my BGP neighbors. We've told it to redistribute routes. Let's jump back on here. We now have received routes in here. So before we didn't have any entries for this, but we've received a BGP route. The route distinguishers, importantly, the VRF targets all line up. So we've now imported those routes. Customer A. Right, so the 188 network here has been advertised as a EVPN type 5 route into the rest of the network. So that's taken care of the networking requirements that would typically be done by the networking engineer, and we've done that through a management interface that is running in isolation from what the vSphere admins typically would see. And we also take that network definition customer A servers and we publish that into vCenter as well. So here is the address space here. This is a read-only instance. The tenant, the operators of vSphere or vCenter are unable to make changes to this. We expect all network changes to be driven by the networking team within inside the NSX-T manager, either through the GUI or through API calls. We can attach a workload to this. So I've got this test server here. Let's attach him to this network. Customer A servers, and we'll jump on the interface, the management interface of this thing. Have a look. Right, so it requested a new IP address. When we change networks, it bounces the interface for us and re-requests an IP address through DHCP. It should still be working. I tested this before. Okay, so that 192.168.188.1 address is the gateway address. This is configured with inside the logical routing instance that's sitting inside the host. So if I spun up that host on, he is on 2. So he is sitting over here. Let's change. He's sitting over on this host here, and he's plugged into the tier 1 router that's sitting here. So when you request, say, ARP for the gateway address .1, the local copy of the tier 1 will respond to that, and then it's then responsible for forwarding traffic across the network using the overlay, either to other hosts on the network or down towards the gateway edge VM, because it has complete visibility of the routing table for its tenancy. If there was any security to be enforced as well, we would enforce the security directly in here as well. So layer 4 firewalling, IPS, etc. Right, take place directly here. So no traffic can actually leave this virtual machine without passing through a security policy if we have it configured, and likewise traffic can't enter the fabric without passing through the firewall, which is actually called the gateway firewall at that point. So we've now managed to successfully build our entire tenancy. In our case, we have 2 virtual machines, sorry, 2 hypervisors. This could be hundreds of hypervisors across multiple data centers. We can also integrate this with bare metal as well. We can look at the topology. We should have a representation now in here showing me exactly what we built. We have 1 VM that's connected here as well. We have it connected to our segment, which is this segment here with the gateway address. We've plugged him into his own dedicated gateway logical router, and then we've connected him into a VRF. You see some IP addresses here. These are all just internal addresses we use for the tunnel overlays. And this customer VRF is connected into the peering router. Peering router is connected upstream using BGP. So this is how we achieve complete logical overlay on top of an existing IP fabric. At no stage here do we log into any switches or routers and actually configure additional VLANs. In fact, we didn't even configure a VLAN at all for this new customer. I could configure customer B, C, D, or beside this. They would all share the same logical tunnel infrastructure. We automatically take care of the isolation. We automatically enforce security closest to the workload. We're not forwarding traffic across the network to a physical firewall or a virtual firewall running somewhere. The same goes for other security instances or security services. The same goes for load balancing, address translation. All the features of a network are baked into the kernel essentially on the hypervisor. Right, so that's essentially it. If you need to get hold of me, feel free to email me. Right. Right, and that is our EVPN lab for today. Have a good day, everyone. Thank you. Bye.